And the notebook for practical session here. Okay, so start. So please feel free to interrupt me either online or here if you have any questions. Yeah, sorry. Did you say something? Okay, so please ask your question or say you have a question on the chat and then I try to hear you. Okay? Let's say so. Okay. So I'm Chloé Braud, and I'm a senior researcher at IRIT, so here in Toulouse. So it's a Toulouse Institute of Computer Science. And I'm working on natural language processing. And so today I'm giving you an introduction to natural language processing. So it's really all the basics about NLP. And then you'll see in other classes much more advanced topic. So yeah, so that was a slide I was using to start my course before last year. I was saying that, yeah, you know, we don't have yet good AI, so we don't have yet good chatbots, except from the ones you can see on some websites. So from now, everything changed, kind of with ChatGPT and Gemini and from a Bard and all their siblings. But yeah, not really everything changed from our respect, but many things change. At least for when I talk about my research topic at Christmas, people kind of know what I'm talking about now. And they say, oh, it works at last. So one thing we can wonder is it still interesting to take a course in natural language processing now? We have all these nice tools. So if we ask Gemini, so it's not Bard, I have to change the name. So it will say yes. Yes, because there's a high demand in industry and academia, and also because there are still many challenges in NLP. So I ask about challenges also to see what he talks about, and it's quite accurate. So he says that generative AI are really good at creating human-like text, but NLP provides a foundation for generative AI, and the foundation you need to understand that we have a specific object to study, language. It's not something like, it's very specific research object, and you have to take NLP courses to understand language and to understand how this AI works and what we can do to improve them. Also, how can we understand the behavior. And so the important thing is they say they work together. So they want to collaborate with us. They are very kind. Okay, so what I'm going to talk in this course is first, what is natural language processing, broadly speaking. I'm going to talk a bit about the specific features of natural language, because it's really something specific. It's very different from images, for example. And so we have all this domain in human science called linguistics or language science. And we need to know some things about linguistics to do natural language processing, at least I think so. Then I will talk a bit more about practical NLP, how to find data, prepare data, and a bit about machine learning. But I will stay on very generic things about machine learning, because you are going to have more courses about neural architectures, neural learning with my colleagues. And I will talk a bit about applications and the challenges we are facing now in NLP. And the practical session will be about sentiment analysis. So we will build a small classifier to identify a sentiment using, like we said, classical NLP, so not neural NLP. So you can build very easily a very kind of efficient classifier without any errors. So what we call natural language processing is this research domain at the interface between linguistics, because we are dealing with natural languages, the languages spoken by humans, you know, as opposed to computer languages, right? Also computational sciences for algorithms, mathematics, because we are using statistics for learning. And also a bit of physics when we are dealing with speech processing. So I'm not doing speech processing at all, because for now we have like a split between NLP that is more for text and speech processing that is for speech. Even if now we are trying to combine both domains. Because now we are trying to combine everything, in fact, also images and videos and everything. So it is considered a subdomain of artificial intelligence, and what we are dealing with is human-machine interaction, so definitely ChatGPT, but also human-human interaction. So we need to extract information that was written by humans and present it to other humans. So we want to improve the access to information, because we have like a lot of data everywhere, and it's very hard to mine the data, you know. And we the second goal is also to understand. So it's like application is maybe the main goal of NLP, but the second goal is also to understand how language works, to better understand how our brain works. Okay, because language is clearly part of our brain behavior. So we have these two aspects. One is more practical. We want to create tools to process text data. So to analyze, to understand, to generate. There's also some application dedicated to save languages, so endangered languages in the world. So, you know, we have about 7,000 languages in the world. And for now, we have not so bad tools for about 100. Okay, and we have languages that disappear every year. So one aspect could be also to save language for some of us. And a second goal is more theoretical. So it's the idea to use empirical methods, so machine learning methods, to better understand what is language, how does it work, and how people in the end understand each other. That's kind of magic for me. Okay, so a more visually way of thinking natural language processing is that we want to take data, so text data in some languages, and more specifically, we want to take all data available. So it's not only well-written text in news or Wikipedia, but also what people write for real in forums, in social media, and it's clearly not the same language. It's not written very you know, there are a lot of mistakes and some new words, and I don't like to speak about mistakes, but different spelling of things. And we also want to consider all the languages of the world, even the sign language, when we have researchers working on it. We want to process this data in some way, and we want to develop applications. So, you know, many of them, like translation is maybe the graal of NLP, but also correction. I mean, the first application developed for in NLP was spam identification in our mailbox. So it was a very useful one, but a very basic one for our regards. And the second goal, as I said, is to understand language. So what we are going to try to explore today is what does it mean to process language data, how we do that, and the challenges that we are facing when trying to deal with all this kind of data. Why NLP is hard? So this is an example from, so it's quite old now, but there was a system called Watson that was supposed to do question answering. So it's a game called Jeopardy, I think, where people have to answer questions. And so they tried with the AI. This time it was a very basic one. But the idea was, okay, we can try to do keyword matching. And so in blue, you have a context. So the text where No, it's a question. So in May 1898, Portugal celebrated the 400th anniversary of this explorer's arrival in India. So you have to find who is the explorer. And the computer find the text where it's written, in May, Gary arrived in India after he celebrated his anniversary in Portugal. If you look at the keywords, so you have this celebration, you have this May, you have anniversary, you have Portugal, so you have India. It seems like a good match. But of course, Gary is not really the explorer we are looking for. And of course, the answer was Vasco da Gama. And if you look at the right document in the corpus, you have the text in green on the 27th of May, 1498, Vasco da Gama landed in Capa Beach. So here you don't have the same keywords, right? You have to understand that you have this temporal, you have to analyze the temporality of both accepts, because you can find that there's 400 years differences between these two texts, okay? So it says that you arrived in 1498 and we are celebrating the 400th anniversary. So you have to do this fine-grained analysis in the temporal aspect. And you have to understand some kind of paraphrase, okay? Because, so he said, where is it? Capa Beach. So you have to understand that Capa Beach is in India. And arrival is not said, but you have landed. Okay, so you have like synonyms, kind of synonyms. So it's very hard for a computer to understand all these things. Other examples of why NLP is hard is that you have ambiguity. There's a lot of ambiguity in languages. We are talking about some of it later. You have this problem, what we call the co-reference entities. So when you say coronavirus, blah, 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 the virus, blah, 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 it, you are always referring to the same thing, okay? Always to coronavirus. That's what we call co-reference. And it's a very hard task, in fact, for machines to understand that all these entities are linked together. The same with elderly people, they. And you have so many form of sarcasm and irony and things like that. So if clients say, like those guys are very helpful indeed, in general, it doesn't mean that it was very helpful. Okay, so often people say that to say the contrary of what they think. Okay, so sarcasm is very, very hard for a computer to understand. And all the phenomena linked to negation and contrast theory are also very hard. So saying that this mouse is not good looking, but it works perfect and I like it. Here it's very difficult for a computer to say, to understand whether the review is positive or negative, because it's not good. So I don't like it. But you have a contrast that reverse the first feeling and say that we like the product. Okay, so all these phenomena are hard to understand. Other issue with when you are studying languages, that language is evolving. So we are creating new words. We are very, very imaginative in creating new words. In fact, it's really something that evolved a lot with time. Syntax and the way we form sentences stay kind of the same across time. Of course, there's an evolution, but not as fast as for vocabulary. So this, what I said before about mistakes. So speakers do not always master their own language. So even if you take this tweet from Donald Trump, you have many errors or misspelling. And speakers are very creative. So it's the same kind of phenomenon than creating new words, but we also create new way of saying some expressions, in fact. So, for example, you will know about lol, MDR in French, or YOLO, etc. So it's way of saying things that we create in general for a generation of people. Right? We also love to add letters and portrait things or improvise with smileys. So all these things are hard to process for a computer because they are new. So when you learn your model with some data, you can't understand the new things that are going to, except if you find a way to build very robust model. So now I want to present you the different levels of linguistic structure. So it's a way we analyze language, starting with phonetics. So I'm not going to talk about phonetics because, as I said, it's more linked to speech processing, and it's like almost a different domain because it's based on physics, and you need a training in signals and all these things I don't know about. So phonetics and phonology. Then you have morphology. So morphology is about how words are built. And it's where we are looking at the creativity of people. Syntax is how sentences are built. So how with these words, we create larger spans of text that we call sentence. And the nice thing is that with a finite number of words, we create an infinite number of sentences. Okay? We are able to say a sentence that has never been pronounced before at any time. Then you have the semantics. So semantics is about the meaning of words and utterances. So what you mean when you say something. And pragmatics is about the meaning in context. So what you really mean, considering who you are, where you are, what are the people around you, and especially in dialogues when you are interacting with other people. And the thing is, in language, at all levels, you have ambiguities. Okay, so for example, lexical ambiguities is when you have a word that can be that can have different meanings. So if I say I saw a duck, it could be in French a canard, so the bird, or the verb about like in the first picture. Syntactic ambiguity is about how we build the sentence. So here the ambiguity is on the way spans of words attached to each other. If I say the chicken is ready to eat, it could be that I'm going to eat it, or the chicken is going to eat. So it's very different meaning, right? And it really depends who is ready to do something. Okay. So in NLP, we have some basics operations that are linked to all these levels of linguistics. And we have what we call the pre-processing that are in general needed for many applications, because you have your text with many words, and we want to have something that is more normalized or more easy to process. Okay, so we are going to do some pre-processing like tokenization, sentence segmentation, or normalization. I'm going to go over these different operation now. One thing is, it's something we used to do a lot, but we are not doing anymore, mostly. So now we have these models. So I don't think you already heard about word embeddings and things like that. I think it's the next courses. Okay. So now we have specific models that are built where each word is associated to a vector, a numerical vector. And when we give a sentence to this system, it automatically builds a representation of our words or sentences. So in fact, it already kind of gives different representation of words, even if they are not very useful for us. And then there's a process to weight this representation. So it's less important to do some pre-processing now. I'm going to go back on that later. But I think it's important to understand what is done in this pre-processing, because it's also used for other applications. So the first step is what we call tokenization. So here, the idea is that we want to recognize words. And so it might sound something very simple, but what is a word? It's not so easy. So we can say it's characters separated with a blank, like when we see a line of text. we can say that it's a sequence of characters with a space or a line or a punctuation. But then what we do when we have an apostrophe, do we say that we have 3 words in I don't know or 4? We don't know. It depends. There's also the problem with multi-word expressions. So like in spite of, is it 1 word or 3? In French, we have the famous pomme de terre. Is it 3 words or just 1 thing and then 1 word? You also have the same thing with proponents. San Francisco, Tour Eiffel, are there 2 words or just 1? And in some languages, it's even harder than in French and English. It's not a huge things, but in German, you have this sequence. I'm not going to read it. And it means the law for the delegation of monitoring beef labeling. So it is not the problem of having too many spaces, it's the problem of not having enough space, okay? You probably don't want this awful thing to be 1 word, because then you have like too many words in your vocabulary, and you want to be able to understand that, I don't know, the law for the designation of monitoring beef or lamb labeling are not 2 different words. They are 2 different expressions with very small. So, and in some languages, you have no word boundaries, so no blank space. So in the case in Chinese, for example, you have an example also on this slide. And of course, we need to separate what we can understand as a word is linked to semantics. Okay, so it's a minimal unit of meaning, right? So in Chinese, in German, and in all languages, you have this minimal unit of languages. It's not because it's like linked in the text or not, but it's different things. So the first step is tokenization. And yes, you have to decide on some rules, and it's the job of linguists. Right? Then the second step is to decide on what is a sentence. So a sentence is a sequence of characters, spaces, punctuation, and in the computer it's all encoded in the same way. Okay, so you have to find these boundaries. In fact, it's very important because sentences are the input we use for many systems. So in general, we need to give sentences to our system. But what is, so you could think that the dot is a very natural way of splitting sentences, but in fact, it's very ambiguous. And for example, in the Wall Street Journal, 47 of the periods are for an abbreviation. Okay. You also have decimal points, ellipses, in email address, and you don't want to split email address in different sentences, right? The other punctuation marks are less ambiguous in English, but they may appear in other things like quotations, emoticons, computer code, etc. So if you need to split a text into sentences, in fact, you need the context. Okay, so here in October, you need to understand that you are not done, that there's other thing after, and so it's not a sentence boundary. M also for Mr. Obama is not a boundary because you are talking about Mr. something, someone, etc. Then the last step is normalization. So the idea of normalization is to improve generalization. So if you look at the main words in the raw data, so the cloud you have on the left, you see that the main tokens, so the most frequent ones, are like and, to, of, the, was, where. So these are tokens that are not really important, right? They are not. They don't carry any meaning, in fact. So they are just what we call grammatical words. They are used to introduce a noun, to decide on the tense of a sentence, etc. What we need is to find the meaningful words in your data. So on the right, you see that the main words are now tree, report, wind, etc., because we removed all these grammatical words. So this is a way to normalize your data. It's just to remove what we call also stop words. So very frequent words, but without meaning. So you have to be careful because there are many lists of these stop words, but maybe for your application, some of these stop words are are important. For example, you have words such as because or while that are included in the stop words because there are conjunction categories that are considered like grammatical categories, but they are useful to understand, for example, the meaning of the reviews we have in one of the first slides. You need the but, okay? You need the but to understand the sentiment in the review. So you have other form of normalization, like one is simply to lowercase everything. So removing the uppercasing will lower the number of different words in your text. And lemmatization is also used to normalize. So instead of having all these different forms like is, was, were, being, you always have be. So it makes for a more simple text. Of course, you lose some information about tense, but you have less words in your vocabulary. So again, this part it's less useful for new models because it's kind of included in it. So I'm going to talk really briefly about language models at the end of the presentation, and you will hear a lot about that in the next courses. But in these what we call language models, so the thing on which things like GPT rely on, you have version with cased or uncased, meaning that you removed all the upper cases or not, for example. And we have also other mechanisms to deal with unknown words, because it's a really important problem for these models. Okay, so so I'm now going to talk about other processing. So it's linguistic processing that we can do on your text and that can provide important information to better analyze your data. So some of them are, I'm going to talk about kind of all of it. So part of speech tagging is about morphology, word disambiguation is about lexical semantics, name entity recognition is kind of semantics also, syntax parsing, of course, syntax, and discourse parsing is more about pragmatics. So it's all the main levels of analysis. So for all these, so what we call tasks, we have now statistical models. So before it was done with rules, so heuristics, but now we have statistical models for everything. And so the performance are kind of varying with like the last ones being more difficult because it's high level. So I'd say outside of the circle of linguistic tasks, linguistic level, sorry. And also it's very, the performance really depends on the languages you are evaluating. Okay, so most of the performance you can see are for English and for well-written English. So in general for like Wall Street Journal English. And if you try your model on, I don't know, Twitter data, the performance will be like lower, much lower. So it depends on the language and the domain. So part of speech tagging is a task where you associate a morphosyntactic category to each word. So the morphosyntactic categories are these things we were taught during our school, like nouns, verbs, pronouns, adjectives, etc. So for example, here for this sentence, she sells seashells on the seashore. You have a pronoun for she, and then a verb, and then a noun, and then a preposition and determinant, and another noun. The problem here is that we have ambiguity, like everywhere in for language. So for example, this example comes from Chomsky, the very famous one, time flies like an arrow. Here you can have different interpretations of the sentence, depending on which morphosyntactic category you choose for each word. Okay, so time could be a noun or a verb. So if you choose noun here, time flies like an arrow. Donc le temps vole comme une flèche. Time is something that is flying, like an arrow. If you choose to see time as a verb, so now you are like using a device to time some flies, like arrows, extra. Okay, so you have different. It's very important to understand that choosing the part of speech will decide on the meaning of the whole sentence. You don't have the same meaning if you change the part of speech. So that's why this ambiguity is very crucial. Okay. So the state of the art here for English is very high for part of speech tagging, and for most of the languages, it's also very high. It becomes very harder when you have not well written text. Okay, so on Twitter, for example, you have very lower. So I give here a link to some state of the art so part of speech is here. Okay, so here is the state of the art. It was in 2018, so it's already but here it's a Bentley Bank, so it's Wall Street Journal. Here is on social media is about 93, so we already lose 4%. Here is another model, but it's kind of good too. Yeah, I'm not sure we have the scores for French. No, but I think it's also kind of high. Okay, so another task is called name entity recognition. Is a task that is studied a lot, and the idea is to identify specific entities in text. So here you can see in the text the persons, the companies, locations, dates, etc. And you need to type them, so saying it's a person or a company, etc. And sometimes you have also to link them. So here the state of the art is really depending on the difficulty of the task. So it depends on the number of types you choose. So it could be only person, organization, location, and list. So often the case. But if you want to find something more fine-grained, then the performance will be lower. Now the task of syntactic analysis is about grouping words into phrases and then phrases into sentences. So what you have to understand is that a sentence is a hierarchical organization of words. Okay. So in fact, if you have a very complex sentence, like you can make beautiful constituent trees, all these phrases, beautiful constituent trees, can be replaced with just one word, donation, right? So if you can replace this group with only one word and this word is a noun, you say that you have a noun phrase. The same with the second sentence, you make something, you can replace make something with fly. So all these things, make something, can be replaced with just one verb. So it's a verb phrase. And you can do the same with an adjective phrase. Okay, you place a very long group with two adjectives and adverbs by just one adjective. So it's an adjective phrase. Okay, so you have a hierarchical organization with groups of words. And then you can represent this organization with trees. So on the left part, and you see digital trees, it can be replaced just by trees, for example. So it's a noun phrase. And then make digital trees can be replaced with just fly. So it's a verb phrase, etc. Okay. So these constituent trees allow to represent the hierarchical organization of words. And on the right side, you have another representation, another way of representing the same information, but it is called dependency trees. So you have here the link between, so it's more a functional view. So you have the link between the verb and you, the subject here, and you say that the type of relation between them is subject. Okay, here you have the link between make and is in trees, and you say that the type of link between them is trees. And you say that you have a head word in the text, in the sentence, sorry. In general, it's a verb. And then you try to find the dependence of the verb and the dependent of each word recursively, okay? And these structures allow to make inference on the content of the sentence, and especially to understand who do what, who does what, and where we are going, etc. So for syntactic analysis, you have ambiguity also. So it's the same example as for part of speech tagging. Depending on what part of speech you chose at the first step, you don't have the same syntactic analysis, right? Because if you choose time to be a noun, you can have only the first of the second one. And if you and if you choose time to be a verb, then you can have only the last syntactic analysis. Okay, and here the syntactic analysis gives you the semantic interpretation of the syntax. They are represented with these pictures. So yes, there's a second interpretation. The second interpretation I didn't talk about is when a like is a verb. So the time you have some kind of time flies. Who loves hours? Okay. So this syntactic analysis can be used to correct errors in text, to do some semantic analysis, so identifying subject, adjunct of an action. It's also used for generation, because if you know what kind of structure you want, you just have to put some words that have the good part of speech tag, etc. And so the state of the art is also rather high for English and for well-written text. Now, if we go to semantics, so here for words, you have one task called words disambiguation. So here the problem is about homophones and homonyms. So homophones is not really an issue for us because it's just words that pronounce the same, but the writing doesn't have to be the same. The problem is homonyms. So we have the same word with different meanings. And so we have, depending on the meaning of the word, we don't want to use the same part of speech, okay? See, if I'm using head as a noun, my part of speech tagger needs to understand what meaning of the word it was before deciding on the part of speech. In general, it's mostly the other way around. But it means that your part of speech tagger has to understand some semantics. And it makes the task harder. So this task is very hard to understand the different sense. And in fact, the problem is mostly in the definitions, in the definition of the meanings of words. Okay, so we have this thing called WordNet, where you have meanings for different words. And it has been made by linguists. And it's very, very complicated. You have like hundreds of senses for one word, but some of them are really rare or very, very, very specific to some domains. And when you try to disambiguate following these definitions, it makes for a very hard task. So that's why I call the granularity. It really depends on how many senses you define for a word. Okay. And then the last level is what I call discourse. So it's when you go beyond sentence boundaries. So most of the NLP tasks are limited to sentences. So in general, we give a sentence as a basic unit. But when we try to read a document, a full document, a text, you notice that there are some relations between the sentences. So for example, there's an explanation, a contrast. Okay, I don't know what it was. So you have links between the different sentences in the text. In fact, a document is not a random sequence of sentences. You have links, okay, it's a coherent thing. And so I already talked about co-reference. So you have these links between entities. You also have temporal links, of course. So events are ordered in text. You also have topic links, Okay, so you are talking about something, then you are going on subtopics and then going back to another topics, etc. And you have also what we call discourse relation, that are these contrast, explanation, or like you are saying something like your thesis about a topic, and then you are giving an argument or an example or a counter argument, etc. Okay, so these are all the way to organize a full document, and so it gives many new tasks for in NLP. So one of them is co-reference resolution. So what I also showed before, you have to understand all these links between entities. So here it's a system called neural coref that gives also the probability the system found for each link. So in gray, you have the links that he tried, but he decided not to output, right? So he found that what was so she is linked to Nina with the higher probability, for example. So you have to find expressions that are linked together, that are noun to other nouns, or noun to pronouns, or pronouns to other pronouns. Okay, and so the state of the art was about 80, but it's probably better now. And for discourse, so all these links, such as I said, explanation, contrast, etc., between sentences. So it's very crucial because it could help to better perform some tasks. For example, for question answering, if you have a text such as the train derailed, there were 4 wounded people, the driver was going too fast. In fact, it's very hard for a machine to understand a link between the first and the last sentence, because it's like a long range relation. But if you want to answer the question, why did the train derail, you have to go 2 sentences after, you know. You have to understand that the driver was going too fast, that was the train derail. So discourse parsing is about finding these links and finding, in fact, the kind of structure you have in the upper right. So it's a very hard task, and it's maybe 60% now for the state of the art. And it's also useful, for example, for sentiment analysis. So, for example, here you have a review of a movie where you have in green all the positive words, and in red all the negative words. So most of the systems for sentiment analysis just count the number of positive and negative words in reviews. And here, these reviews would be assigned with a positive grade. But if you read the review the full review, you see that at the end, so it's positive, blah, blah, blah. And at the end, it said, but other than all that, this movie is nothing more than hidden reports. And in fact, by the but, he reversed all the sentiment about the review that was the positive aspect of the review that was given before. So just because of this last contrastive relation, the review is in fact negative for the movie. Okay, so using discourse parsing, we could find that we have this concession, what is called concession, so a contrastive relation, and then find the good polarity. Okay, so that was about linguistics. Is it okay? No question? Okay. So, okay. So yeah, so just if you want to play with some data and try some NLP, you can find many data sets online. So NLTK is a old library to do NLP, but there are some data sets available. So scikit-learn is the library we are going to use in the practical session, and you have some data sets also, some toy data sets, but it's interesting. On Kaggle, you have many challenges linked to NLP, and you can find many data sets to play with. So LDC, Linguistic Data Consortium, is a resource for datasets, but you have to pay, so less interesting. And it's kind of expensive. You have also, I give you also a list of NLP datasets I found in GitHub. And one thing you can do also is simply to go on teams working in academia on NLP, and you can find many corpora. So the second one is a French one, a French linguistic laboratory, and they provide a lot of resources. So just as an example of what is a task, what is an example of an application in NLP, when you want to do sentiment analysis, what you have as input is what we call the review, okay? But in fact is a text, and the texts are of varied sizes, okay? So it could be just a few lines, and it could be like 100 lines, very, very long things. It's written by anyone, so you can't really say, you can't really guess that if the text will be well written or not. So the task is to classify each review as positive or negative. So in fact, the task could be also three categories. So it could be, there could be also a neutral category, and it could be also more fine-grained. So if you go on a review website, sometimes you have stars, like 5 stars, or sometimes you have likes, so like on social media. And so you have to convert these stars into classes or these likes. So here is the way you design your, so you have a task you want to classify the sentiment of a review, but in fact you have many decisions to make just before starting to do some NLP and machine learning. Okay, you have to decide, for example, if you want to limit the type of text you are going to take, and the number of classes you want to have in your system. So for the practical session, it would be a binary task, just positive, negative, but it's a decision I made. Okay, so here are 2 libraries that are used, often used to do some pre-processing. So as I said, NLTK is kind of old now. So it was developed by people in academia and mostly for teaching, in fact. So you can really modify things in the code and tweak things and test many different algorithms, but it's not very practical. You can't really use it in industry. SpaCy is more applicative, so it chooses the best model for you. You don't have to decide many things, any things, in fact, and it's very easy to deploy. So I think we'll see that in the practical session because we can't see anything. So just to show you that it's kind of very easy. So the first line is doing, the sentence. Then you go through some what they call the pipeline. So the pipeline is called NLP here. And then it's done. You have the tokenization. So here the tokens are printed. And then you can also do at the end, it's the sentences. Okay, so just a line of code, and you have your tokenization, your sentence splitting, extra. We'll see that during the practical session. And the part of speech is also very easy to perform, just 1 line. And if you look here, so it's time flies like an arrow. The system only gives you 1 answer. Okay, so I told you that this sentence was ambiguous, but the systems here decided to give you only one answer, and it's time as a noun and flies as a verb. Okay, so here it's this kind of models are not meant to deal with ambiguity. They have to choose. So the example using NLTK, I'm not going to talk about it. So now if we want to learn something from this data, so a bit of history, in the 80s, NLP was dominated by symbolic methods. So we were writing rules. So for example, what we call regular expressions, so like a pattern matching to do tokenization. So the advantages is it's that it was based on linguistic expertise. So it was very precise, but it was very hard to adapt to new data. So there was a lack of coverage because you can't think about everything. And it was very time consuming, especially if you want to develop something for a new domain, for a new language, etc. The second step is in the 90s, so statistical approaches, so what we call now classic machine learning. And here you have different libraries, but scikit-learn is really easy to use, so it's the one we are going to use. And here, in fact, the idea is to learn the rules automatically, okay, rather than writing them. And it's, in fact, we are going to learn linear functions of our input. So here it's really faster to train, and there are still, in fact, very good baselines for many applications in text. For images, it's definitely better with neural methods. For text, it's less clear. And so since 2010, NLP field, like other fields, is dominated by neural methods. So neural learning is still machine learning. It's still statistical learning. Sorry. Sorry. So I'm going back to instructions. Là. Okay, so I was saying that neural methods are really still machine learning and statistical learning, but just based on different architectures. And the main difference is that now we don't have mostly or mainly linear functions, but we combine linear and non-linear functions. And so the introduction of non-linearity is really the thing that makes neural methods more powerful. So in general, we have improved performance compared to what we call statistical approaches, but they are very hard to interpret. So it's what we call black box. And so it's very harder to understand the decisions. So here we have many libraries, and yeah, I don't know what you are going to use during the next courses, but it's probably based on Hugging Face, which is based on PyTorch. So just a reminder about what is machine learning and in the supervised setting. So what we have, it's like input data, what we also call the training set. So we have on one side data point, so what we want to classify, for example, these two pictures, and we have labels attached to these data points. Okay, so for example, the first picture is a cat, the second one is a sandwich. Then the goal of machine learning is to build some function. So in fact, to approximate the real classification function, what we call here f, and this function is then used to predict a label on new data. So for example, the last picture that is part of our evaluation set, and then we predict a label, and then we compare this label with a gold label, so the real label, and we compute a score for this system, for the model. So we decide if the function is a good approximation of the real classification function. The problem with text data is how to represent this text. Okay, so because the computers don't understand text. Okay, computers only understand numbers. Okay, so it's only 1 and 0. So we have to transform a sentence into a vector of numerical values. And it's the main issue, right? Then we can use any algorithm we want. So one way of doing that, and it's what we did for many years, is to have one vector where each dimension in the vector is one word or one feature in our feature vocabulary. And if the word or the feature is present in the document, then we associate a specific value at this dimension. Okay, it's what we call bag of words. So, for example, here we have this sentence: the elephant sneezed at the sight of potatoes. We have this vocabulary, so all the words we know. The vocabulary is all the words we know in our data. So here it's a very simple model with only 18 words. Okay, so first we build this vocabulary, and then we look at the words to see if they are present in the sentence. So for example, the elephant is present, so we have 1, and then here elephant 1, sight, sees, extra 1, and so we have 1 for all the words that are present in the sentence, and 0 for the other ones. Okay. So this vector is a representation of our sentence. This 1, 0, 1, 0, 0, 0 extra. Okay. So it's very easy to build and easy to use. So now your computer can read your sentence, so with this vector, and it comes with varied flavors. So this flavor is the binary one, 1 and 0. You can also use raw frequencies. So for example, here we could say that Z is present 2 times, so we are using 2 because it's repeated, right? And we have some kind of normalization where we are trying to weight the words depending on their importance. So, for example, the is present 2 times, but as I said before, it's not a very important word in general for any task. So we are going to say, okay, it's a very frequent word. It's frequent in our sentence, but it's also very frequent in all our data. So we don't want to weight this very high. On the contrary, a word like magnificent is really rare and probably crucial for a task. So we want to give it more weight because it's not present a lot in our data. So we want to give it more importance. So this is what is done with TFT, just in the intuition of the computation. So in fact, we can do bag of words, but also bag of any features. So for example, we can represent the presence of some post tags in our input. So in fact, we used, so I say used, but it's still used in some way, but we use this representation with any kind of feature. So we say, okay, we think that for this task, it's important to know that we have a verb. So we are going to add a dimension in our vector saying we have a verb or not, okay? Or we have a specific syntactic relation, or we have a name entity, etc. Okay? So it was very easy, just adding new dimension to represent our input. But it comes with some issue. And the main issue is that it's very high dimensional. So in this example, it was only 18 dimensions because it's easy to read. But in fact, we have like 100,000 words in the language. So we have to deal with vector of 100,000 dimensions. And for a computer, it's very hard to deal with very long vectors like that. It's what we call the curse of dimensionality, meaning that if you have many dimensions in your input vectors, you also need many parameters to learn good functions. And in fact, you need many data. So there were many solutions proposed. One was to ignore specific words. So as I said before, we remove the stop words. For example, we only keep the most frequent words or the most, like the one that seem the most important ones. Or we try to group words into semantic categories and have these categories instead of words. Another issue is that bag of word representation ignore the words, the order of the word, and the context. So if you have a sentence like, I don't know why I like this movie, it's clearly not the same meaning as I don't like this movie and I know why. But if you look at these two sentences, it's exactly the same words, simply ordered different way, okay? And in one case, it's positive, and in the other case, it's negative. If you do sentiment analysis, it's crucial to understand this difference, okay? And with bag of words, it's completely, I mean, it's what we call bag of words because we put all the words in a bag and we mélange. Another solution is to use n-grams instead of words. So n-grams are a combination of words. So the bigrams are two words. So we are going to have bag of bigrams. So instead of having like and not, we are going to have not like and like this extra. But the problem is it's even more dimensions. So it doesn't solve this first issue. Okay, and so the solution will be given with these word embeddings I talked about earlier and that we are going to explain a bit later. So during the practical session, we are going to use scikit-learn to do some sentiment analysis classification. So scikit-learn is a toolkit for machine learning in Python that was developed in France, at INRIA. And it's non-neural architecture. It's only the classic machine learning. But you have the implementation of many algorithms, such as naive bayes, logistic regression, SVM, very well-known classification algorithms. And it makes it really easy to pre-process and vectorize text data and to optimize and evaluate the models. And you can also do other things than classification, such as clustering or regression. And if you see this piece of code, it's what you need to transform your input text into a bag of words. So for this line, vectorize, it's the line that transforms your text into bag of words. This line, train your model. And this line makes a prediction, okay? Like in 4 lines of code, you train the model and make the prediction. Okay, so it's very easy and very fast. So if you want to play with some NLP, if you want to do some NLP to play with data, you should first experiment with this code before trying again face and all the transformers and nice neural architectures. Okay. So you probably know that NLP is used for many applications. So as I said, the first one was spam filtering, and it works quite well now, right? And it's a very nice application. So also spell checking. So we all used to use words and we were very happy that all the words were corrected when we type. Automatic translation is really useful, I think. Finding information in text is, I mean, applications like Google and etc. are based on NLP techniques. So you have some more specific application like entity recognition, as we talked about. You have many tasks about classifying some text. So finding the topics, so finding all the documents that talk about specific things like football or economics or things like that. And you have new tasks that develop this in recent years, such as fake news detection or harassment detection, sexism detection, etc. You have many applications about analyzing opinion or sentiments, especially for companies that wish to understand why their product is not liked by everyone. What they should change in their product or their way to present it. So, and then you have also applications that are like more generative tasks. So if you want to summarize some text or to simplify some text. So simplifying text, for example, is done for people who try to learn a new language and they want to have simplified words or simplified sentences, syntax. Also for people with specific cognitive impairments. So for example, for children with dyslexia, things like that, you have people who works with simplifying text. You have application that poses some issue with ethics, such as profiling users, so done a lot, or detecting some mental illness. So in fact, you have more and more companies and other academic fields that are interested in NLP techniques. And so, yeah, just to remind the different types of tasks we have for machine learning. So the classification is to assign a category to an object. So the main example is PAM classification, and you have also a word sense disambiguation because it's assigning a meaning to a word in context. Classification of books, sentiment analysis is also a classification task. You can also have language detection, fake news detection. You have also some application about lie and fraud detection, for example, in scientific publications, so something very pure. And you have also other applications that could pose some ethical issues, such as gender, political detection, etc. So this is about classification. Now there's another learning task that is called sequence labeling. And in this case, the idea is that we want to take into account the context, so the surrounding words. So if you think about the task of post-tagging or name entity recognition, if you want to take a decision about a word, the decision is in fact dependent on the decisions you took for the previous word and the decision that you are going to take for the next word, of course. But you, in fact, you need to look at the decisions you take for nearby elements. Okay, so saying that de here in Arc de Triomphe is a place depends on the fact that you already decided that Arc was a place. Okay, so this kind of so it's still a classification because for words you assign a class, but since the classification decision is dependent on previous ones, we call it sequence labeling. Okay. Or I think in the interface it's called token classification. It's a bit confusing for me. So you are going to see that, I think, in the next courses about recurrent neural network. And another task, so another learning task is what we call sequence to sequence. So in this case, you have a sequence of words, and you want to have the target is also a sequence of words. It's not giving a class, assigning a class to a sequence of text, is assigning another sequence to the source sequence. And the main application is translation. Okay, so you have one sentence in one language, and the target is another sentence in another language. You also have this setting for question answering, because you have the question and in general context, so a document associated to the question, and you have to find the answer. Summarization also, you have text to summarize, etc. All the text corresponding to generation. And for this specific setting, clearly neural methods have allowed massive improvement. So this graph is about machine translation progresses in the last years. And since we are using neural machine translation, we have large improvement. I added some application in medicine, so it's not my main domain, but just, yeah, because I thought it could be of some interest here. So there are increasing demands in applying NLP techniques to medicine data, to medical data. And often it's about analyzing free text. So I'm not sure what's meant by predicting patient trajectories, but I know about, one paper that was about trying to identify cancer in clinical notes. Don't ask me more about that. I don't know the details. I know also about people who contacted us to try to find all the treatments, all the analysis applied to some patient in an hospital to better find the cost of this patient, because it seems to be some classification of the patient depending on some algorithm, and it depends on people having well crossed some cases in the paperwork, and they want to have some machine learning techniques to help with that. There are also some more and more study on studying linguistic markers of, for example, cognitive impairments. So for dementia, for schizophrenia, for example, where the idea is to try to identify what change in the use of language when you have some cognitive impairment. So it's not about detecting people with cognitive impairments, but to understand the modification in the way people talk and interact with each other. There are also many studies about identifying group of entities that participate in some relationships, such like chemical-induced disease, protein-protein interaction. So there are many works on that. And also another thing, another aspect of the application is in generating text. So for example, there are people who want to build interface for patients to ask questions about their treatment. Also generation of reports directly from some radiology reports, and also about simplification again. So trying, I kind of like this paper, trying to make patient-friendly clinical notes, because yeah, patients often don't understand everything in a clinical report, and they think that they should try to make something simple. There are many issues in NLP for medical data, and the main ones are privacy, ethics, and also bias. So for example, I work on some data with people with schizophrenia, and we found that all the patients with schizophrenia were students who talked a lot about their studies, and all the people with schizophrenia were patients who talk a lot about their disease. And in fact, when you try to identify the two groups, you only find people who talk a lot about their disease and people who talk a lot about their master studies, and it's a bias in the way we build the data. So you have to be very careful when you annotate the data and when you build the data to not induce bias in your data. And another thing is low source data. So I'm going to talk a bit about that later, but you don't have a lot of data for medical data because it's very hard to obtain, very expensive. And in general, it's very hard to work within this domain. Okay, so so why we are using neural methods? So you are going to see that in next lectures. It's because they introduce this non-linearity. So I talked about that a bit already. So the limits of this, what I call classical statistical methods compared to the one we are using now, is this linearity, is the problem with data representation, and the problem of word similarity. So the problem of linearity is that many data are non-linear, in fact. So linearity means that methods that we are using within scikit, so the method we are going to try during the practical session, what they try to do is to find a line between the two sets of data, right? So it's a line if we are in 2 dimensions, it's a plan if we are in 3 dimensions, etc. But it's a surface that will split the data into 2 spaces. But most of the data are nonlinear, and by introducing a nonlinearity, neural architectures make it possible to find this kind of decision function. So this is one issue. As I said, bag of words have many issues. So the data representation based on bag of words, and especially we have to find good ways, relevant ways of representing our data. And linked to that is the problem of word similarity. So if we have bag of word representation of words, it means that for apple and pear, we will have these 2 vectors. Okay, this one, the first one represents the fact that we have 1 at the dimension of apple, and the second one we have 1 at the dimension of pear. Okay. So it's what we call the one-hot vector, only 1, 1. It's easy to implement, but it means that if we take the vector representing these words, there will be no difference between these 2 vectors and the vector representing apple and the vector representing car. Okay, it means that these vectors don't represent any notion of similarity between words. Okay, and if we take the distance between vectors, for example, using cosinus, something like that, it will be always the same. Okay, it will be 0 because they are orthogonal, right? But what we want, it's to have vectors that represent that pear and apple are kind of more similar than to car. Okay, that's the goal. And how we can do that? So the way we do that is based on a really old idea, comes from the 50s, and it is called the distributional hypothesis. So if I give you this for examples, so delicious soluceps, sweet soluceps, stale soluceps, and freshly baked soluceps, and if I ask you to guess what is a soluceps, I think you don't know what is a soluceps, right? But you can guess, I think, that is something we eat, okay? And if okay, so this is a soluceps, so it's just the name of speculoos in Belgium. But at least you are able to guess that it's food, okay? Just looking at these different examples. And this is because you have this distributional hypothesis, meaning that the context of use of a word is useful to guess its meaning, okay? So because it's used with words like delicious, sweet, that are in general used with food, then you can guess it's food. Okay? It's the idea at the basis of what we call the word embeddings. And so the word embeddings are the idea that we are going to represent the meaning of words based on their context of use, okay, on this idea of distributional hypothesis. So it was already used before neural networks. And the idea was we are going to build a matrix over all the words appearing in the corpus. We are counting the number of times the words appear together, so delicious and something. And then we will get some vector representation for each word. So in general, we do some dimension reduction just to have some smaller vectors, but it's the idea. So now what we are doing to build these vectors is to train a neural network directly to build the representation. And it's what we call the language model. Okay. I think maybe you already heard about language model, large language model, very large pre-trained language model. So GPT and all are language models, okay? And what they are, what is a language model is just a representation of the words as vectors. And in the general as low dimensional vectors, so not 100,000 like the bag of words, and with continuous values. So it's not like 1, 0, 0, 1. It's values that are like real values, okay? It's not binary. So here, just visually, you can say that even if it's not real numbers, but just colors and squares, apple and pear are closer to each other than to car. Okay. So we train neural network to build these vectors using massive, and when I say massive, really massive amount of data with some task, okay, because it's a machine learning system, so we need some tasks. And in general, the task is to predict some linguistic units, so mostly predict a word. So a model like GPT is trained to predict the next word. Okay, what we call a generative model. It's going to predict the next word. So you give it a few words and it predicts the next and the next and the next. Okay, and this is a task. So you need we can do that now because we have this massive amount of data and we have the computational resource to train these models because it's very huge. So you said you have billions of parameters to learn. So here is an example of a model, but I think you are going to see that in next lecture. So just the intuition is we have this example, the quick brown fox jumps over the lazy dog, and we try to learn brown, giving to the model the quick fox jumps. Okay, so the model has to predict the word in blue, knowing the words surrounding it. Okay. And inside the neural network, you have these vectors that are going to be learned. And what is very nice with this representation is that it allows to make some inference using the vectors. So for example, so it was this paper, I didn't put the title of the paper, but they showed that from king to queen, you can do a king minus man plus woman. Okay. If you do this, the operation with the plus and minus on the vector, you find the vector for queen. Okay. So you remove man from king and you add woman and you have queen. Okay. And you have also some vector transformation that gives you some information about the verb tense. So you have a representation, a vector transformation that goes from the gerundive to the past tense. And you also have this semantic information that goes from one country to its capital city. So it's that's good. You see that the vectors are not perfectly aligned, but it's quite good. So here it's a tool to look at embeddings, but I'm not going to show you that, but you can go on your computer. And it projects a cloud of words. You can simplify it to have it on 2 dimension or 3 dimension, because you can. It's I think it's about 200 or 200 dimensions, so you can't process it with your brain, but you can project on 2 dimensions and see that, for example, actor is a word that is very close to actress and other words about movies. So data representation before neural network was very hard to find a good representation of our data, but now we just feed our machine learning system with these word embeddings, but we still have many decisions to make. So which word embeddings we are going to choose, and also, so I said that we have word embeddings. So how do we represent a sentence? How do we represent a document? Building using this word representation is still a question. And other question that arise now, it's what about all the other information we used to have, like part of speech tagging, syntax, etc. So is it already implemented in our word embeddings, or do we want to add that in some way? There are also many questions about different languages. So many of these language models are developed for English and for a few languages. So as I said, we have like 100 languages covered. What do we do with these 6,000, 900 over the languages? Knowing that it costs a lot to develop these language models. So I don't think it will be possible for all languages and for all domains. So in general, it doesn't work very well when you change a domain. And we also have many problems with evaluation, how to know that these embeddings are good. So we still need some experts to better understand that. Another challenge we have to face in NLP now is the fact that annotating data is very hard, very expensive, and very time consuming. So we have data for many things, but often it's only a few data. So there are many solutions that are proposed to try to deal with this lack of data. So most of them are like extension of supervised learning to other settings. So for example, you have distant learning where you try to learn from noisy annotations. So it was done, for example, with sentiment analysis in tweets, where they use the emojis as annotation. So if the emoji was smiling, it was a positive tweet, and in the contrary, a negative one. So it's very noisy because you can use a reverse emoji for your tweet. But with the mass of data, you hope that you will have some good effect on your system, and it works. You also have transfer learning, like you try to, for example, when you try to identify depression, you can think that identifying emotion is useful. So you have more data for emotion. So you try to transfer your model from emotion to depression to improve your task. And you have also many applications to try to go from one domain. For example, I don't know, you try to learn a good model on news data and you want to adapt to medical data or something more specialized. So this is called domain adaptation in general. Other challenge we have is using different modalities. So as I said, now we are trying to combine speech and text, but also images or even videos. So for example, here you have Video BERT that is used to automatically illustrate a set of instructions in a video. And the last issue is interpretability and explainability. So it's a very active domain where you try to understand the decision of your model. So it's very important because now AI is used, I mean, in many aspects of our lives. So even people try to use it in laws to make decisions, and you have to understand why the model takes your decision. Even also for medical data, it's very important to understand why the model said something. So it's a very active research domain. Other issue as the reproducibility of our systems and the sharing data and the cost. So the cost in terms of money, but also the cost in terms of how do you say cost d'empreinte carbon footprint. Carbon footprint. Thank you. So here on the upper side, upper right, you have the cost of a transformer, of training a transformer with a neural architecture, and it's more than like 6 times using a car, or using 6 cars for a lifetime. So it's very it costs a lot. And the last issues are with bias and fairness in NLP data and models. So you have gender bias in many models. So this one is, I don't know if it works, it still works, but it's Finnish to English. So in Finnish, you don't have this distinction between he and she. The pronoun is the same for male and female. But if you try to translate to English, then clearly the system makes choices that are sexist. Okay, he invests, but she washes the laundry. He's playing sport, but she takes care of the children. He works, she dances, he drives the car. Okay, so he decides who is a male and who is a female based on the activity. You also have racial bias. I think you all heard about this AI that begins to be racist in like minutes after having been put online. And you have also other reference for your interest. Oh yeah, it was it was an AI that was put online it was an association who decided to replace the human people helping people with eating disorders by a chatbot. So it was in 31st of May, and like I think it's 2 days after they decided to remove it because it was giving very bad advice to people seeking help. So yeah, it was recommending to count calories and strive for a deficit of up to 1,000 calories per day, etc. So it was a very disaster. So we are still not yet ready to use AI everywhere, right? Okay. Do you have any question on no? Okay, great. And online, I lost the chat. Where? So you can go on. So you have a notebook. Where are you? Here you have a notebook, so it gives you access to Collab here. And when you are here, you need to do a copy in your drive. Okay. You need to save a copy in your drive to work on it. You don't have a computer. Okay, so you open the Collab notebook, and then you have to save a copy in your drive, and then you can work on it. Okay, so je vois rien du tout. Donc la première partie, c'est juste essayer de faire des pré-processing. The first part is about making some pre-processing with Spacey, and then you have to build a sentiment analysis classifier. I mean, you have to build most of the code is given. Je vois rien. Je vais l'ouvrir là. Okay, so you managed to make a copy? Yep. Okay, so the first part, you just download some data. So I don't know if you already used Google Colab. Yes. So then you can just continue. You have this part about pre-processing with Spacey. So you will see how it works to make to do the tokenization, the segmentation into sentences. You also have the name entity recognition and the syntactic parsing. And then the second part is about sentiment analysis. So we will just focus on classification. I don't think we'll have time to improve the results. And then if we have time, we'll do the third part is about trying to generate some world embeddings. So it's a library that allows to generate from any text, from any corpus, your own world embeddings. So I let you try to make it run, and if you have any question, you ask me. Normalement, ça vous affiche le token, ensuite le lemme, et la partie. Ça, c'est des parties simplifiées, on l'a dit tout à l'heure, donc il faut aussi bien pour la petite, pour la guerre, une personne de l'événement, c'est non propre aussi. Vous avez différents. You have different sets of post tags depending on the system you use and depending on the annotation of the data. So here it's a very simplified set of post tags. You may have until like 70 or 100 different post tags. It really depends on linguistic choice when they annotate the data. I don't remember if there are errors in the post tagging. Often you have errors when you have different languages. So in French, often we use the English words in when we write some text. So this is very hard for the system. And for Americans, there are a lot of words in Spanish, and it's also very hard to for the system to switch in different languages. But I think it's quite good. Yeah, then the second step of here, just the Panda data frame to see to have a better visualization. So it's really more beautiful. So there's a post tag and tag type. Oh yeah, so the post tag here is it's tag sets from the French event. So one of the first data sets on page with post tags. We have something more complicated. You see FRB is for left rounded bracket, I think, something like that. And RRB, so they have more detailed aspects. Which is all punctuation for the text. Okay, so there are some errors in here it's just about what is done for negotiation. And yeah, there are some errors sometimes when we have some issues with tokenization in general. I completely. Yes, so Turing, yeah, when Turing was turned into a verb here. Our non-Turing, that it wasn't recognized as a proper noun. So it's a strange mistake. And there's also some issues sometimes when you have the citation, so the numbers into brackets. So it's a problem with tokenization. And if the tokenization fails, when the post tagging fails, and if the post tagging fails, when the syntactic parsing fails, and yeah, everything fails. So we have this error propagation, so it's very important to have a good tokenization at the beginning. So yeah, here it's just about having an explanation of the post tags, because if you don't know all of them by heart, it could be hard to understand. And then the second step is to segment into sentences. So here we are. Here are some errors. So I don't remember what the sentence 10, but yeah, so here should have split here. But where you put all these parts, you can see that there are two sentences. So it means that if you try to give that to the syntax parser, it will be a big fail, okay? Because we have two sentences in fact. You could probably have some troubles dealing with it. Okay. Then the task of name entity recognition. So as you can see, it's always like a few lines of code. So it's very easy to process your space. So here you give your text and it gives you the different entities you have. So an organization, AI is an organization, but that's for why. Alan Turing is a person, so here it works. Good. And you have also like there was some strange things, I don't remember way. We got date also. Organization. Oh yes, you have this nice visualization.
We put the one as a target and not an order.
Oh yeah, yeah, yeah. And so this George Turing said this is an organization. It's kind of strange to say that. And here you have a person that puts in the strange name. And I think that the initially church, because church is here more advanced, but I can't find it. I think it was saying for an organization or for location, church. I can find it here. Make it right side. Okay. The church was the organization instead of person. You can't see where. But it works quite well. Okay. You can try with something like Twitter data. I mean, I think it will be harder to get good results, but with this data, it's okay. So it's a model that is designed for domains such as, I mean, here it's Wikipedia, but it won't work out of the box for, like, for example, medical data where you have very specific entities. So you have some, like for post tags, you have different sets of types of entities, and it depends on the domain. And so you have models that can transfer from one domain to another domain, but it's very difficult because you have these different type of these different sets of entities. And now syntactic parsing, so the same. It's very easy to do it with Spacie, and you have this nice visualization. So it's the example in the slide. But you can see with longer sentence, it's kind of harder to understand what's going on. So yeah, this one is very, very long. Okay. And so we should have one root, but I can't find it. So somewhere you have a root. Not find it here. Oh, and you can also navigate the tree with so here is the data frame, and you have all the relation between the parts of the sentence. It's useful if you want to do some. It could be used to do some information extraction because you have who is doing what. Okay. And for the second part, we don't have so much time, so I mean, all the code is in the data with many explanations, so I hope you will manage to understand by yourself. But here you have the code to read the data. Okay, so it's a data from Kaggle, but I just do some pre-processing to have some cleaner data and to have some to balance between positive and negative reviews. So here's the code to read the data. Okay, so you can see you have reviews with the sentiment associated. Okay, so 0 is for a bad review and 1 is for a positive review. Okay. So it's always very important to look at your data before doing any machine learning task, right? And so the second part here is about feature extraction. So we are going to build a bag of word representation, such as the one I presented during the course. So as I already said, it's very, very easy to do that with scikit-learn. So I think it starts here. So you get an object called a const vectorizer, and it's really the thing that is going to give the bag of words. So it will const all the words in your training set, and then assign a vector representation to all your input instances. So here I just have this element called max features, because I want to limit myself to 1,000 words. So it will take only the 1,000 most frequent words in the data. It's mainly done to have something that's fast to train for you. So you can remove it and you can try with like 5,000 or 10,000, it should be better. 1,000 is really low. And then you have this code, so fit transform applied to train view. So fit means that we are going to count, build the vocabulary. So when you do some machine learning, closer to my mic, when you are doing some machine learning task, you have a training set, and all you know about the world is your training set. Okay, so it's very important to understand that you really have like a world, and it's your training set, and you don't know anything else. So in particular, all the words you know are the ones in your training set. You don't know any words that are not in your training set. So you train your system to do some tasks based on your training set, and then you test on some data you don't know. The dev set, because you are trying some different things and you want to evaluate different settings. And then at the end, and only at the end, the test set. And the test set is what we call unseen data. And you don't look at the data, at the test data before the end of the process. When you are sure you have the best model you can have, you test it on the test data. And it's the moment where you test if your model is robust enough to be applied to new data. If you look at your test data before, you cheat. It's cheating. So one important thing for NLP is that there are some words that could be unknown at training time because it's new words, or just because your training data is not really representative of all the data in the world, because you don't have enough training data or something. But I mean, it's the problem with your data. It's not a problem that you are going to solve by looking at the test data. So if in the first part, in the fixed part, the model look at the training data and decides on which words he knows. And if he doesn't know the other words, okay, so it will assign a specific representation to all the words unknown to be able to compute some scores, but you don't want to, you don't know the words that are not in the training. So the fit is about building this vocabulary, and the transform is about transforming as an instance into a vector. So when you are transforming the dev set later on, I don't know where this factor, you only use the transform part and not the fit. Okay? Because if you use the fit again, you compute a new vocabulary and so on. Okay. So here the fit transform is building the vocabulary and vectorizing the data. Here it's just a part about looking at what is done with vectorization. So you have the vocabulary that are all the words in your training set. Okay. Here all the words in my training set, and what we get, it's exactly what was in the slide. Okay, it's a large vector with 1 and 0s. Okay. So here the bag of word representation of one review. Okay. And just to be sure, you can check that the word here, the fifth word. So I look at it, and it's this word, and it's a word that really appears in my first review. Okay, just to be sure that what we did is correct. Now we prepare the dev data, and as I said, we only use the transform function here. Okay. And finally, we can do the classification. So I called it classification without neurons because it's not neural methods. I'm using some classic algorithm. So here it's logistic regression, which is called accent. And so the same way, it's very easy inside it. So you define which algorithm you want to use. Here I want to use logistic regression. And then I use this method called fit, and fit is the same as train. So fit is doing the training. So here, first fire the fit. I train my model on the training set, and now I can do the prediction on the depth set. Okay, line of code and train and predict. And I can print my scores here. So this model has an accuracy of 84, so it means that it makes the right prediction in 84% of it. Quite an easy task. So yeah, this report gives you all the metrics you need. I mean, this accuracy, and you also have the score per class. So it's clear to see that you have the same score in fact for classes, and you also have the same number of examples in each class. So it's what we call the balance data sets. We have the same number of instances in both classes. It's the easiest setting, but in general, it's not the case in a realistic setting. So I'm not going through the improving the results. It's just about modifying data representation, using TF-IDF normalization, using n-grams. So all the things I talked about during the course, the lecture, and here's about finding the best model. So making some variation in some parameters of the models to try to improve the performance. And at the end, we can give the results on the test set. Here's a way to test other algorithms, such as naive Bayes. And here, it's a way to look at the prediction, and more specifically, look at the weights given by the model to different words. And so if we look here to the features with highest weights for the positive class, we have great, perfect, fun, excellent. Okay, so it makes sense. So it's a way to explain the decision of our model, something we can't really do with neural architectures. And if we look at the top features for the negative class, we have bad, worst, poor, awful. So the most negative weights are linked to the negative class. Okay. And the last part was about generating Braud embeddings. So we don't have time to look at it in details, but so it's a really nice library to generate word embeddings. And when you have word embeddings, you can compute similarities between numbers. So for example, it was a data set made of cooking blocks. So it's all about cookies. Oh no, it's not. No. This one is made with the reviews. So here you can find that the words that are most similar to actor or actress, all performance, actor also, character, etc. So it makes sense. So it seems to have learned something, even if our data set is very small. And here for actress, I suppose. No, it's so here it's the same thing as king and queen thing. So with actor, so actor minus man plus woman, and we look at the most as the most popular word for this operation vectors and actress. So first to make some operations on the vector. And then you can modify the model with different things in trial. Okay. And I have just a note about some of these models being better for rare words or for very frequent words. Okay. Any questions? No, it's about you. I'm surprised. Okay. So if you have any question on NLP in general or on this lecture, don't hesitate to send me an email. Okay. And you online? Sorry, I forgot about you. No question. Okay. Bye bye.